If you would recall, last time we introduced the idea of a vector field. This is going to be the new thing that we have moving forward. A vector field is a function whose output is a vector. To each point in our space, we are assigning a vector. This is a big leap forward for us. For a long time, our functions have been outputting scalars. F of x, y, and z, to each point, we assign a scalar. That sentence changed right after I named the function. I realized I didn't need to name the function. But for a long time, our outputs were just scalars. When we first started studying functions, y equals f of x, each input, x, produced an output, y, that was a scalar. That's what we dealt with for a very long time. And then here in Calc 3 is where we start talking about multivariable functions. Z equals f of x, y. We only changed one thing, the number of inputs. What we were doing with z equals f of x, y is to each point in R2, we were assigning a real number, a scalar. What we're going to do now is to take each point in R2 and eventually R3 and assign a vector. So here's some notation that we can use. Notice that the name of the vector field has an arrow over it to say we're making a vector field. I mean, you look at the definition of our vector field and you're like, oh, yeah, that's pretty obvious, dude. There's the I and the J. And then down here, there's the I, the J, and the K. But there it is. We want to make sure that when we're talking about a vector field, we name it as a vector. Note that our components, F1, F2, and F3 for our vector field in R3, those are scalar functions. Each coefficient or each component is a scalar function. So they don't get the arrows on top. Everything looks much cooler when you have arrows on top, but if you really want your math to look cool, have arrows on top for some, but not arrows on all of them. Then you need to start integrating stuff because integrals are the cooler looking math. So here we have our scalar functions. These are the components of the vector field. So the components of our vectors are going to be scalars. And we will usually name them this way. I'll use capital letters for our vector fields with an arrow on top to make sure that we all know that we're talking about a vector field. And then I'll use an indexed version of that name for the component functions. Remember, what we're doing is assigning a vector to each point in R2 or R3. We are assigning a vector to each point in R2 or R3. That's our input-output game here. For those of you following along in the book and think this hasn't come up yet, this is in 17.3. As I am prone to do, I like to start in the middle of the chapter because sometimes math books take a while to get to the point. I'd rather just start there. Rather than slowly build up to something. You know what I mean? I realize that at times in the past, I have slowly built up to things. Sometimes it's a Marvel movie, sometimes it's DC, where you take a third of your runtime to introduce your character. And you do it in the sloppiest way possible. With like a picture of the character and then like a little dossier on the side. You're making your audience breathe. You know what I mean? Everybody see Suicide Squad? I watch DC try to be making movies. And I think, man, this is awful because this looks like all my D&D campaigns. At the core, there's a great idea, but the execution is just awful. You should have spent more time writing. Anyway, what are we talking about? Oh yeah, vector fields. We got to think about what we want to think about with vector fields. Here are the two things that we want to think about with vector fields. The vector field itself, we want to think of our two favorite examples are going to be water flowing around at the surface. That could be our thinking for a vector field in R2. Or think about the flow of air through the room. So thinking about vector fields. We need a way to think about vector fields. And the two pictures that we want to bring to call to mind that we're going to use a lot, the surface of water. If I have a vector field over R2, think of a vector field in 2 dimensions as the flow on the surface of the water. We can think of the surface of the water as being a 2-dimensional thing. And the vector field will indicate the flow at every point, what direction the water is flowing. We can think about a vector field in R3 as the flow of air in a room. At every point in this room, air is going in some direction. The vector field is just telling you what direction the air is flowing. This is the first place we want to stop when we are thinking about vector fields. Just what's going on? What can we see? What do we see in the flow on the surface of this water? What do we see in the flow of the air? That's our first stop. Think about how things are flowing in our vector field. What is the vector field doing to the water or the air? The next thing that we want to do, the part that we want to impose on this, We want to start putting stuff in our vector fields. Once we have an idea of what the vector field is doing, we're going to start sticking stuff into the vector field and then making calculations. Because of course we're going to be making calculations. This is the math class. If you didn't think calculations were going to show up, man, you're in the wrong math class. So next we want to think about the stuff that we're going to put into our vector fields. We want to think about a one-dimensional path through our vector field. Maybe a boat cruising along the surface of the water. The boat's trying to get from one side of the water to the other side of the water. It can't just leave itself up to the whims of the vector field. It's going to have to carve a path through the vector field. So imagine a boat on the surface of the water. It's going to make a one-dimensional path through the vector field. Now this one-dimensional path we can draw on the two-dimensional surface of the water. We can also imagine a one-dimensional path through three-dimensional space. So we're going to imagine at every point in this room, a vector indicating the direction that the air is flowing. And now we can put a one-dimensional path through the space. And we can just imagine a fly flying around. In both cases, we can imagine that path being helped or hindered by the vector field. Sometimes the boat is going to be trying to go against the current, and at other times the boat will be going with the current. So imagine the boat or the fly being helped or hindered by the vector field. The fly flying through the room, sometimes the air will be pushing it along, and sometimes the fly will have to fly into a headwind. But we're imagining this one-dimensional path in the vector field. So this one works for a vector field in R2 or R3. This is the kind of thinking that we'll have to apply in R2 or R3. Once again, we're imagining the vector field sitting here, and we were just sticking stuff into our vector. Let's think about the calculus components that we're going to need to deal with this before we move on to our second bullet point. Are bullet points called bullet points in other places in the world? It seems like a very American thing to call them. Because they're not even shaped like, they're not shaped like bullets. They're shaped like bullet holes. And I just keep wondering, like in Texas or something like that, let's move on to bullet number 1. And they like actually shoot a hole in the paper. And then like write down the next thing. Bullet point number 2. Why bullet points? Why gotta be so violent? Anyway, what are we talking about? Oh, yes. Let's talk about the components that we need. So in calculus, we do 3 things. In calculus, we do 3 things. We do derivative stuff, we do integral stuff, and we describe stuff. So in the describe stuff category, we're going to have to figure out a way to describe these one-dimensional paths. So calculus stuff. Here's our to-do list. We're going to need some way to describe these one-dimensional paths. Once we describe these one-dimensional paths, we got to think about derivative stuff. Derivative tells us instantaneous rate of change. Derivative is going to tell us the direction of the path. Once we describe all the points along the path, we're going to need derivatives to describe the direction at each point on the path. We'll need derivatives to describe the direction along the path. At every point on that path, the derivative will tell us what direction we're headed. Then we need to think about integration. We know that integration is multiplication, but one of the factors is continuously variable. So we know that integration is multiplication. You want to remember that integration is multiplication, but one of the factors is continuously variable. It didn't translate want to. I said wanna because That's how we talk. And it just transcribed W-A-N-N-A, wanna. I'm both pleased and betrayed by this. Integration is multiplication, but one of the factors is continuously variable. What we've got going on here is a vector field, and we've got a path with a bunch of vectors, right, which is going to be described by a bunch of vectors represented by the derivatives. So we got to think about what we have available for integration. When vectors are in play, our multiplication options are dot product and cross product. So in the integration category, we're going to be dealing with dot products and cross products. We need some multiplication for our integrals. Since everything is vectors, our multiplication is going to be dot products and cross products. Our multiplication is going to consist of dot products and cross products. We have two kinds of multiplication when we're dealing with vectors. So because we're multiplying vectors, we're going to be dot product and cross product. Those are our options. If we think back to our setup, the way we want to think about our vector fields, and then putting stuff in our vector fields. In this category, we're putting a one-dimensional path through our vector field in R2 or R3, represented by a boat trying to sail through the vector field, or some fly trying to fly through the vector field. And we're imagining the boat or fly being helped or hindered by the vector field. That is, at each point, the fly trying to go one direction, the vector field going in another direction, we want to know how much the vector field is helping or hindering the fly. I want to know how much of the vector field is going in the direction of the path. And so that's what our dot product tells us. This is that dot product thinking coming back. We want to think about the dot product A cross B as how much of the vector A is going in the direction. Sorry, did I say dot or cross? I have to start over. In A dot B, we're trying to calculate how much of A is going in the direction of B. How much of one vector is going in the direction of the other vector? That's exactly what we need here, because I've got a vector field and I've got a path through that vector field being described with vectors. And I want to know how much one vector is going in the direction of the other vector. So we're going to be calculating a dot product. And this dot product is going to be continuously variable because at every point we have a different vector. We have a different vector from the vector field. We have a different vector from the direction we're trying to go. And we are trying to multiply those two things. In the cross product, well, we'll have to think about this for a little bit longer. But for our setup, flow of water, flow of air, path through, this dot product seems to be exactly the right thing that we need. Any questions? How's everybody okay? Today's okay because we're like we're just talking about what we're going to be talking about. We're just framing things right now. Kind of the hard part of building a house, kind of the easy part of setting up a sequence of talks. So let's go back to our original question. Now that we've got this simmering on a back burner, I know I've asked you to simmer a lot of things on a lot of back burners. The math stove has lots of back burners. There's like one in the front and like 70 or 80 in the back. All right, let's take that, put it on the back burner, let it simmer for a while. We've been putting stuff into our vector field so that we can make some calculations. We started off with putting a one-dimensional path through a vector field. I put the one-dimensional path in the two-dimensional space or the three-dimensional space. So number two, I'm just going to do the same thing we always do. I'm going to go from a one-dimensional thing to a two-dimensional thing. Now I want to take this one-dimensional path, and instead of putting a one-dimensional path in the vector field, I want to put a two-dimensional surface in the vector field. We're going to need some space for this surface, so I'm not going to want to put this two-dimensional surface in the two-dimensional space. It would just cover everything. Might be something there, but more importantly, we're going to take this two-dimensional surface and stick it in our three-dimensional vector field. So this one is really more of an R3 thing because we need the space. So we're going to go into our three-dimensional space. We're going to imagine the vector field is the airflow around the room, and I come walking in with a net. I didn't actually bring a net. So a net, a two-dimensional surface. I'm going to stick it in the vector field. And what I'm going to want to measure is the vector field flowing through the surface. What happens if the surface is flat like this? What happens if the surface, let's see. What happens if the surface is flat like this? What happens if it's bent? I know I don't have 3D here, but what happens if it's bent? What if I had bent it this way? Will that change how things go? I just want to imagine this is like a net or some kind of filter, some kind of membrane, and the air is flowing through the membrane or the net. Should have just started with the last one and covered the first two. Oh well. faced with the same to-do list. Describe stuff, derivatives, integrals. What are we going to do? Describe stuff. We're going to need some way to describe these surfaces. So our to-do list is the same. Well, we're describing a surface in R3. Sometimes we can use a function. That's where we started with this business. But it's going to be some kind of equation in X, Y, and Z describing the surface. So we've got something for that. That's not actually new. We already got that one. Back to this one-dimensional paths. If we need some way to describe one-dimensional paths in 2- and 3-dimensional space. Sometimes we can use functions. That's the one we rely on the most, y equals f of x. But we don't always get to use that. So some kind of equation in x and y. Oh, wow. Some kind of equation in x, y, and z. We're going to need to use derivatives to describe some direction along the surface. What kind of direction are we going to get from the surface? That's a little bit weird. Where are we going to get vectors on this surface? We're going to get vectors on this surface. That's a little bit weird. Once we have vectors on the surface, our thinking is going to go back to this multiplication for integrals. So once we have vectors, this one's a little conditional right now. Once we have vectors on this surface, then I can start having this multiplication. I got the vector field. I got vectors on this surface somehow. I can start multiplying those vectors with dot product and cross product. Once we have vectors, once the surface has vectors, then we'll be able to multiply. Once we're multiplying, integration shows up because one of our factors will be continuously variable. Any questions? This is the thinking that's going to be behind our calculations for the rest of the semester. Because we're building up to the fundamental theorems of calculus that are all, we need to adapt our fundamental theorem of calculus to deal with these vector fields. Any questions? All right. So this seems like a lot because it's a lot. You haven't seen how long this goes, but you know that we just started chapter 17 and the book does go all the way to chapter 21. So you might be thinking, that seems like a lot to kind of cram into the end of the semester. I know we're only in the second half, but that's only because it seems like a lot to put in. So usually what happens in Calc 3, it kind of gets season 8 of Game of Thrones. I don't know if that's a verb, but it's a verb now. Season 8 of Game of Thrones. It's just like, oh, we're running out of time. Just cut it off now. You know what I mean? Kind of like drop a lot of stuff. Get the big picture. Have the big set piece. Hope people don't think about it too much. after you show it, realize that they're going to think about it, and then Game of Thrones doesn't exist anymore. Any questions? Has anybody started watching the new Game of Thrones? House of the Dragons? I haven't seen any of it, so no spoilers, but what I have seen kind of looks like this. Really annoying. What I'm saying is it's too dark and everybody whispering. It's too far into the filmed media style of acting. You know what I mean? Like in a movie, that's way more consumed. But in a movie, you can kind of tell which actors were raised to work the stage and which actors were raised to work film and television, small screen. Because in film and television, the camera can be right up, you can do close-ups, right? And we know that that very subtle facial changes can be used to express things. But on a stage, when we're at further range than even this, right, in this classroom, if I want to express something with my face, it has to be gigantic. I can't just do like subtle surprise. I can't do any of it because I can't act, but I can't do like subtle surprise, like, but if there's a close-up, you'd be able to see that I was subtly surprised by something and I'm trying to contain it. But on the stage, I can't just do that. It just looks like people are just standing there. On the stage, you have to indicate with your whole body that you have been surprised by something and that you're trying to conceal it, right? It has to be bigger. And then what happens is you get close-ups of actors that are on the stage and they like just do this big gigantic face thing. It's like, oh, whoa, tone it down. You know what I mean? Anyway. What are we talking about? Oh, yes. So here's our framework. This is the framework of how we want to be thinking about these vector fields as we move into the fundamental theorem of calculus. Fundamental theorems of calculus. I thought y'all were done. You are not. That's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.